Hi, and welcome to the experiment session of the Basic DC course. If you've been reading along, you'll be able to read the literature supplied with the course. What we're going to do is a basic DC circuit, and the first one will be a series circuit, then we'll do a parallel circuit. We have some things to work with here. We have a switch, and it's labeled on and off with some alligator clip leads attached. We have a battery, 9 volt. And we have what's called a breadboard. In the old days, they actually made things on boards used to bake bread. In this case, it's a convenience item. And what you have are little slots with conductive material going crossways on this. Let me do a little drawing here. You have a conductive material, little slot, U-shaped affair. And that resides down underneath these little holes. Then you put your component leads in there, and there are 5 little holes, so you could plug in 5 little leads. What I've done is plug the battery in, plus and minus leads, and I've got a little jumper going down here, so we've got our minus right there, going through the first light, going to this light, going to that light. And of course we have an open circuit. Later on we'll be using the multimeter, which has multiple functions, and we'll explore these as we go along. If you complete the circuit, the lights should light up. Current goes through one, the next one, and so forth. And that's a series circuit, which is battery, a lamp, another lamp, back to the battery. The current is common. The voltage is dropped across each part of this circuit. Okay, now we're going to connect it up in a parallel circuit. Which looks like this. You got your battery, got your 2 wires. There's a light, and there's a light. Voltage is common. The voltage will be the same across this light bulb as it is across this one. Okay. And we'll do our connections. Now they're connected in parallel with each other. We'll use a switch. A switch does the same thing as connecting and disconnecting a wire. Notice the lights are brighter. Okay, series and parallel. Thing to remember, voltage is common in parallel. In a series circuit, current is common. Now, let's get the reading. Open circuit, no light. Closed circuit, light. This is a schematic diagram. It's an electrical symbols representation of what happens. Again, a schematic diagram. This is the series circuits. This is parallel. Now let's explore multimeters. This one in particular. Multimeter can measure a variety of things. The first thing we're going to do is measure voltage. Now you can measure two kinds of voltage: DC voltage or AC voltage, direct current, alternating current. Although a little difficult to see, the AC side has a symbol like that, indicating that the voltage and current reverse directions every cycle. DC, which is what you get from batteries, stays the same. It doesn't change. Okay. Same circuit. Let's set the meter up as a DC 20 volt full scale. DC 20 volt full scale. Well, let's see what voltage the battery has. .84. We've been playing with it a little. It's getting a little tired. So that's how you check the battery. Now, in the old days, when you had a meter movement, you'd have a meter and it'd have a pointer. If you connected it up backwards, the pointer would go whack, slam, bang, hurt, pain. People would frown at you. The new stuff merely whimpers. You get a minus sign in the display when you connect the polarity in reverse. Normally this is your plus, this is your minus. Black is usually the minus color. So let's hook it up in reverse. Plus to minus. And as you can see on the display, you get a minus sign. Zero it. Come on. Oh well, there we go. Do it again. Minus sign, indicating that the voltage is reversed. Doesn't damage the meter. Just a convenient thing to know. If we reconnect these in series, we can read the drop across one light bulb. Now our voltage is just a little under 9 volts, 8.8, so we're not going to read 4.5. We're going to read 4.4 perhaps. There we go. Have our trusty alligator clip to complete the circuit. We'll grab one to give ourselves a place to tie the voltage reference to the minus terminal. And these are the experiments I expect you to do at home so you get a full grasp. And there we are, 4.34 across that light bulb, 4.2, well, something like that. Yeah, 4.36. I think maybe I was interfering a little bit with the connection. That's that light bulb. Let's read across the next one. 4.2. So, there you have it. You're reading what they call voltage drops in a series circuit. If we do this in parallel, of course, we're going to have probably 8.8 volts here. This is the parallel. This is sort of a pictorial. You notice that it's got a picture of a battery and a picture of a meter versus a schematic which uses electrical symbols. Your multimeter can measure small amounts of current also, and we're going to do that next. So if you're following along in the reading, you can see that you set it to the right and down, and it's set to read 200 milliamps or 0.2 amps DC full scale. And you look here, you'll be able to see the amps DC. So let's turn it around. Okay. Well, let's make a connection or two here. There's that connection. Here's the next one. Okay, the current is flowing through the two light bulbs and then through the meter back to the positive terminal of the battery. Much like this illustration. Although there's two light bulbs here, so we have half the current that we'd normally have. Okay. Your meter can also read resistance, reads ohms, so to speak. I have here a couple of resistors. Let's set it up to read ohms. That reads 200 ohms full scale. Here's an 82 ohm resistor. Come on, you. As you can see, that reads pretty accurately. Here's a 1 ohm resistor. 2.2 ohms. Let's try shorting the leads. The leads say 1.3, so it's about a 0.9 ohm resistor. This is at the bottom of its range of accurate reading. Let's do something to read the current, read the resistance in a more sophisticated manner. Let's make a current source. Okay, we've still got our battery, which is down to probably getting close to 8.2 volts now. Let's say it's 8.2. We've got a resistor. This is the schematic symbol for a resistor, 82 ohms. Let's find out what current we can make with the meter. Got our negative lead there. Here. Let's get a positive lead. Set this up for reading current. 99.1 milliamps, almost 100 milliamps. That's useful. I'll show you why. So we have a current source. Will give us 100 milliamps. What do we do with that? Well, we get rid of the meter. Got our same 8.2 volts on the battery. Same 82 ohm resistor. This time we're going to put the 1 ohm resistor here. And we'll read the voltage across that 1 ohm resistor, see what it is. And we need to change the meter back to reading voltage again. In this case we want 200 millivolts full scale. Rearrange this a little bit. Okay, now we have 100 milliamps going through the 1 ohm resistor. And we read 102.6 millivolts with 100 milliamps. What does that mean? What it means is we have the same circuit, 82 ohms. We have 100 milliamps flowing through a 1 ohm resistor. 8.2 volts, let's say. So what we have is a method to determine the resistance of this resistor. We'll use the triangle just to keep things simple. There's your ohms, there's your amps. With triangles, what you do, instead of doing formula transpositions, you cover up the thing you don't know. Now we know the voltage, 100 millivolts, or 0.1 volt, so 0.1. We know the amperage, 0.1. So what we don't know is ohms. We want to know. Cover it up. 0.1 divided by 0.1, that's going to give us 1 ohm. So we can read this accurately by making a current source and using Ohm's law. The reason I bring this up is portable appliance testers use a 100 milliamp source to measure low resistance. So what we're going to do next is do a cord. One of those extension cords. We're going to find out, using the same method, I'm going to put our voltmeter right here and find out what the resistance of the cord is. Let me just grab that sucker. This is to check the earth lead resistance. So we can get our current source back. Look up there. There. Hook up to the resistor. Well, now let's see what the voltage is across the cord. 42.1, call it 42.0, I've got to get a steady bite here. 42 millivolts. Tends to fluctuate a little bit. These aren't the best connections. So we've got 42 millivolts across that cord. with 100 milliamps going through it. Now, let's do our calculation again. Got the same triangle, volts, amps, and ohms. Want to know ohms? So we plug in volts, 0.042. The amps, 0.1. We need to know ohms. 0.042 divided by 0.1 yields 0.004 ohms, or 4 milliohms. And that's how a portable appliance tester or any low ohm meter can measure the resistance of a very low resistance thing like a wire. This concludes our experiments. Hopefully you will repeat these at home and send photos in. Thank you for watching.